When an object is experiencing force, its momentum will be constantly changing. And so to do any sort of calculations about the position of an object under these circumstances, we're going to have to do some approximations. So, for example, let's say that we're trying to track the position of a comet moving around a star. Now, we can go ahead and use the equations that we have, but we just have to make a few modifications. Because as this object moves, that momentum vector has to be constantly changing. And so if we're going to use the position update formula, we've got to be a little careful. The way we do this is we break the motion up into discrete time steps. So rather than treating this as a continuous motion, we're kind of treating this as a series of discrete motions. So at this particular point, we figure out what the force is on the object, and we can calculate a new momentum, and then using that momentum, we let the object move. And so what we're doing is, over this motion, we're assuming once this force has acted at this point, it doesn't do anything over the course of this motion. Now we know that's not the case, but if we choose these time steps small enough, we can then get a very good approximation. So let's take a look at a little bit simpler case where we've got an object moving under the gravitational force of the Earth, and so the direction of the force isn't changing at all. And so you can see what we're doing here is that at each point we are updating the momentum. We're using the momentum update. So right here we're making use of P final equals P initial plus F net delta T. And so here is our P initial. In other words, this is the momentum the object had to get to that point. Then the change in momentum, or the impulse, is coming from this vector right here. The sum of these two vectors gives me my new momentum. Now, to figure out the next position of the object, I'm going to go ahead and find R3. That's this position right here. So R3 is going to be equal to R2 plus V. And now this velocity here is going to be the velocity resulting from this momentum. So V2 delta T, where since we're dealing with velocities that are smaller than the speed of light, we can use the non-relativistic approximation. So this is going to be R2 plus P2 over M delta T. So that gives me my new position here. Then what I need to do is I calculate a new momentum right here. So at that point, P3 is going to be equal to P2 plus F net delta T. And that will give me this vector here. And to figure out the next point, R4, I'm going to use the position update. That's R3 plus V3 delta T, where V3 is due to that momentum right there. So that is R3 plus P3 over M delta T. And we just keep on doing this again and again. This is called the iterative technique, and this will give me a really good approximation, assuming we choose delta T small enough. Now, what we're ultimately doing, we're doing calculus. Because what we're doing is, with small delta T's, we're adding up tiny changes in momentum. And so if you consider something moving over a trajectory, if we break those delta T's up small enough, ultimately what we're doing is calculating an integral. And that's what we have right here. So if we were to integrate from our initial position to our final position, we could figure out what our final momentum is coming from this equation right here. And that's really what the heart of this chapter is, and we will be using these techniques later, so it's a good idea that you get a sense as to how to use these, that you get a good idea of what this iterative technique is. In later chapters, we'll actually deal with forces that change. In this example here, our F-net was actually the same at every single point. In later chapters, we're going to have to calculate F-net at every single point. So it's important that you do get comfortable with this technique in this easier setting so that when we get to the tougher stuff, you don't have any difficulties. Also talked about in this chapter is the spring force, and I wanted to talk about it just briefly. The spring force is a vector, and you can kind of see that because here we have a picture of a spring that's been stretched off to the side, and if you imagine your hand holding this ball, you know that the direction of that pull is going to be back towards the top. If we were to go ahead and pull the spring over here, the force would be up along this direction, and so forth. So the direction of the force depends on which way we pull it. So this L hat right here, that's the vector along this direction, the direction that we've pulled the spring or pushed the spring. This minus sign right here is telling us that the force is actually going to be opposite the direction of L hat. So it's actually going to be up like that. That's my negative L hat direction. Ks says something about the spring. It's called the spring constant. It's the strength of the spring. And Ks has units of newtons per meter. And what that's telling you is for every meter that you stretch it, how many newtons of force is that spring going to pull with? And then the last little detail is this S. S is the stretch of the spring. So every single spring has a relaxed or equilibrium length, which we call L naught. Now this is just a scalar quantity because it's the length of the spring no matter which way you're holding it. It has no direction. It is a scalar quantity. So to find the stretch, we take the magnitude of how far we pulled it from its attachment point minus this equilibrium length. Notice that this is a scalar quantity. This is easy to get tripped up on, but you have to remember to take the magnitude of the L vector minus this scalar quantity, the equilibrium length. That then gives you the stretch, which is a scalar quantity. So this part right here is all scalar. This part is all direction. One last thing that's covered in this chapter is the near-Earth approximation for gravity. When we get to the next chapter, we'll actually see that the equation is a little bit more complicated, but it reduces down to this when we're very near the surface of the Earth. And by near, I mean within a few tens to 20s of kilometers. When we get to the next chapter, we'll talk about the validity of this approximation. So notice here that this is giving us the magnitude. The direction you will have to kind of insert yourself. And typically, the way we set up our coordinate system, we usually assume that gravity is pointing in the negative y direction. So you will actually have to manually insert a direction. This is just giving us the magnitude. So m is the mass of the object, and g is sometimes called little g, or the near-Earth gravitational constant. This is not the acceleration due to gravity. If you've had physics before, you may have heard it referred to as that. That's incorrect because it's only under very special circumstances that an object will have this acceleration. G does have units of meters per second squared. It does have units of acceleration, but it is not the acceleration due to gravity. So try to avoid calling it that. You can call it little g or the near-Earth gravitational constant. Either is fine. And G has approximate value of 9.8 meters per second squared, or if you like English units, it's roughly 32 feet per second squared.